Hi, my name is Fei Yu, and today I'll be teaching a little bit about the theories of special relativity and general relativity, and also applying those theories to the movie Interstellar. So to first give some context about what happens in the movie, Earth is predicted to fall apart because of climate change that's causing extreme weather and also the loss of crops. So NASA has detected that very far away, there's a planet called Miller's Planet, and that planet has signs of organic matter. So they send a few astronauts to go on this spaceship, Endurance, to survey Miller's Planet and see if it's actually habitable or not. And by the way, this Miller's Planet is close to this black hole right here. And this is the movie clip. This is the movie clip that I'll be using.
What was that?
First handshake.
Where? We're here.
So the lost communications came through.
How?
The relay on this side cached them. So years of basic data, no real surprises. Miller's side has kept pinging thumbs up, as has Dr. Mann's. Edmonds went down 3 years ago.
Transmitter failure?
Maybe. He was sending the thumbs up right until it went dark.
But Miller still looks good, though, right? Because she's coming up fast.
Mm-hmm.
With one complication. The planet is much closer to Gargantua than we thought.
Gargantua.
It's what we're calling the black hole. Miller's and Dr. Mann's planets both orbit it.
And Miller's is on the horizon?
Oh, it's a basketball around a hoop. Landing there takes us dangerously close, and a black hole that big has a huge gravitational pull.
Look, I could swing around that neutron star to decelerate.
No, it's not that. It's time. The gravity on that planet will slow our clock compared to Earth's drastically.
Oh, how bad?
Well, every hour we spend on that planet will be 7 years back on Earth. Well, that's relativity, folks.
Well, we can't just drop down there without Cooper.
We have a mission.
Conserve fuel, minimize thrusting, but make sure we stay in range of Miller's planet. You got it?
I wouldn't leave you behind, Dr. Brand.
You ready, Case?
Yep.
You don't say much, do you?
TARS talks plenty for both of us.
Detach. Romilly, are you reading these forces?
Unbelievable.
The literal heart of darkness.
We could just see the collapsed star inside. The singularity. Yeah, we'd solve gravity.
We can't get anything from it.
Nothing escapes that horizon. Not even light. Oh, the answer's there. Just no way to see it.
There's Miller's planet?
Goodbye, Ranger.
So that's the scene in Interstellar, and before, so pretty much in that scene we get to see aspects of time dilation. We also get to see a black hole, and so we're going to be using those two theories of relativity to explain how these two phenomena work. Right, so the theory of special relativity. It was proposed by Einstein in 1905, and it's pretty much about how speed affects time. There's a couple of rules for this, and we can only use this theory when the reference frames are not accelerating, which means they're inertial. And this theory consists of two main laws. The first one being that the laws of physics are the same in all the inertial frames, and that the speed of light is always constant for the observers. And the speed of light is 3 times 10 to the 8 meters per second. So to give you guys examples of how this theory, the special theory of relativity applies, let's say we have a train with a guy on it and a mirror across from it, and this train is moving at half the speed of light. Well, let's say the distance between the guy and the mirror is 5 meters. So when he looks into the mirror, the light from his face hits the mirror and comes back with a total of 10 meters. Now, if we look at another scenario where there's an observer here on a platform watching this thing happen. Now, notice both these frame of references are non-accelerating. This guy is moving at constant speed relative to the train, and this person is just standing still. So special relativity applies here. Now, what this person on the platform sees is that as the light from the guy's face comes out, it would be diagonal because this train is also moving very fast horizontally. So what we get is that this distance right here would be greater than 10 meters. And also remember that the speed of light must be the same, must be constant. So if we calculate time here, we get that the time is 10 divided by the speed of light. While in this case, the distance is greater than the distance that the light traveled is greater than 10 meters, but the speed of light should still be the same. This would make it so that the time would be greater than this person's time. So now we get to see that from different frame of references, this person perceives time differently than this person. And that sums up the special theory of relativity, where the faster you go, the slower you experience time in the eyes of an observer. So now we're going to be talking about time dilation. So we know that time would dilate the faster you go. So we have here standard time, which would be, in this case, the time on the train, and dilated time would be the observer. And this time dilation equation only works when there's some time dilation coefficient, gamma, also known as the Lorentz factor. And today we're going to be deriving what this Lorentz factor is. So say we have a light bulb right here and emits a light particle. And this distance would be the speed of light times time. And at the same time, this light source is also moving horizontally, and some observer here is spectating this thing happen. So the horizontal distance would be the speed v of this light bulb, which is, say, a significant portion of the speed of light. And since this frame of reference is moving with respect to this stationary observer, then the time experienced would be dilated time. As well, since this light bulb is moving, this light particle would not be moving vertically but diagonally. And we know that the speed of light is still c, but since this traveled a greater distance diagonally than it was vertically, then the time also must be dilated. So we shift this thing over to the right here. We actually get a right angle triangle, and we can set up an equation. Using Pythagorean theorem, we get that the hypotenuse would equal to the base squared plus the height squared. Also keep in mind the time dilation equation, where the Lorentz factor is dilated time over time. So keep these two equations in mind. So we have this Pythagorean equation. what I'm doing here is expanding, factoring out dilated time, and solving for right here I'm solving for normal time, standard time divided by dilated time. And keep in mind, if you still remember, that the Lorentz factor is actually dilated time over time, and this is not the same as this. Therefore, we must reciprocate both sides, and now we get the same time differential. So we solve here that the Lorentz factor is equal to this quantity. Now we can actually apply, now that we know the Lorentz factor, we can actually apply time dilation into Interstellar. So we know that in the beginning of that scene, the spaceship Endurance comes out of the wormhole traveling at 100,000 kilometers per second. I found this value online. And that would equal to 1 times 10 to the power of 8 meters per second, which is equivalent to 0.3 C. And so let's say this spaceship was traveling for 1 hour. Then what would that time be on Earth? What would that dilated time be? Well, we use the dilated time equation, and we also use the Lorentz factor. And now we just plug in v squared for this value right here. Now if you expand the power, you get c squared times 0.3 squared. And the c squared would cancel out to 1. And we just solve for the Lorentz factor, and you get this number right here. So substituting this Lorentz factor into the time dilation equation, we get that the dilated time is the Lorentz factor times 1 hour of standard time right here. And the dilated time would be 1.04828 hours. So to put it in other words, every 60 minutes on this spaceship, people on Earth experiences 62.9 minutes. And I think that's pretty cool. And now when they go to Miller's planet, they are no longer traveling at very fast speeds. They're actually on a planet that's near a black hole, and that causes a time dilation as well. I said in the movie, 1 hour equals to 7 hours on Earth. So first we need to understand the theory of general relativity, and it was proposed also by Einstein in 1916. And it pretty much states that the gravitational effect between masses is caused by the warping of space. So we know that Newton also has an equation for gravity right here. And Newton describes gravity as an invisible attractive force between two masses, right? And this equation is actually a special case of general relativity. We know that this equation actually doesn't work for planetary calculations. So Einstein was predicting or theorizing that space is actually a fabric, and when you put a massive object on that fabric, it creates a well right here. This massive object, the sun, creates a well in the fabric of space, and therefore this Earth would fall into this curvature created by the sun. And this falling motion would be equivalent to this invisible force of attraction, equivalent to gravity. And that's pretty much how general relativity works. And also, not only is mass being bent, but time is also being warped when going near massive objects. So, for instance, we have two light beams right here. One is under the influence of a gravitational field, the Earth. And notice how this Earth creates a curvature here. And there's another beam that's not under the influence of a gravitational field, and that would travel straight. So we know that the speed is equal to the distance over time. Now, since under a gravitational field, it would curve, making this distance larger than if it was straight. So we know that c must be constant, and the fact that distance is increasing, time must also increase. And this makes it so that time is not a constant, it's not a variable, it is variable and it's non-constant. And this would suggest that time increases proportionally to the curvature of space, or that time passes slower near a gravitational field. So now we know that going near a gravitational field would cause a distortion in time. Einstein had this equation right here, and he simplified it to give a gravitational time dilation equation. And these are the variables represented in this equation. So before we start doing calculations with what happened in Interstellar, I want to quickly go over the basic premises of a black hole. So in the middle of the black hole, it's called the singularity. And at that point, there's a density of infinity. As you can see here, there's a single point with infinite mass right there. And around this black hole, there's a part called the event horizon. And this event horizon is also known as the point of no return. This is because if you go past this point, then you will for sure be sucked into this black hole. This is because light cannot escape. If you're inside the event horizon, even light cannot escape. That's why it's called a black hole. As you can see here, this black hole, Gargantua, is the black hole in Interstellar. And you can see visibly here the event horizon, and that inside it is completely black. And also, another terminology to know is that the distance from the singularity to the event horizon is called the Schwarzschild radius. So, how do we apply Einstein's gravitational time dilation equation in Interstellar? Well, we can actually determine if the location of Miller's planet is at a plausible location based on the time dilation given in the movie. So we know that 1 hour on Miller's planet is equal to 7 years on Earth. Going back to this equation, we can actually solve for the radius here, the distance between Miller's planet and the black hole. We can calculate this distance right here. Now, if this distance is larger than the Schwarzschild radius, it would put this planet beyond the event horizon, making this planet in a plausible location. However, if we calculate that the radius is shorter than the Schwarzschild radius, then this planet would be inside the event horizon, making it an impossible location. So we first have to find the Schwarzschild radius of Gargantua. So we know that based on Google that the Gargantua has a mass of 100 million solar masses, and here I converted that into kilograms. So we know that at the event horizon, if you go into it, light cannot escape, which means that at the event horizon, the only thing that can escape is light. Being the fastest thing in the universe, only light can escape at the event horizon. So if we use the formula for escape velocity, instead of v, we put the speed of light, and we solve for r here. This r value would be the Schwarzschild radius of Gargantua. We plug in the numbers and we calculate that this radius is this quantity right here. Now we have to calculate the distance between Miller's planet and Gargantua based on the time dilation given in the movie. So to reinstate, 1 hour on Miller's planet is equal to 7 years on Earth. So here I converted that into seconds. for standard time and dilated time. Before we make some calculation, we also have to make some assumptions. And one of the assumptions is that being on Miller's planet would be equivalent to being near a gravitational field, which would mean that there is some factor of time dilation there. But we're gonna neglect that to make these calculations bit more simple. And also another assumption is that the black hole is not spinning. If the black hole was spinning, then it would change the angular velocity and also the orbit of Miller's planet, making the gravitational pull variable at different points of the orbit. So now we got those assumptions. We can use Einstein's time dilation equation. And right here, we're going to be solving for R. So this is pure math, algebra manipulation. And now this is the equation for R. We plug in our values here. We find out that the radius between Miller's planet and the singularity of Gargantua is this quantity right here. So to answer the question, is the location of Miller's planet plausible? Well, we have the distance between Miller's and the black hole is this quantity, and it's actually larger than the Schwarzschild radius, which would mean that Miller's planet is actually outside of the event horizon. So yes, the location of Miller's planet is theoretically accurate. So we can also calculate by subtracting these two values how far this planet was from the event horizon, and we get 200,000 meters. Now that's very, very close. To put that into perspective, the distance between Earth and the International Space Station is twice of this, 400,000 meters. So to summarize, interstellar is actually accurate to some degree. And so respect to the movie producers and the script writers for actually making these calculations and placing Miller's planet in a location that would give such an extreme time dilation of 1 hour to 7 years. So I hope you guys learned something new from my lesson, and thank you for your time.